Hey guys, today we will be doing one of the 3 review questions we received for the AP Physics Chapter 4 Kinematics in Two Directions test. So this is number 79, and it reads, in one contest at the county fair, a spring-loaded plunger launches a ball at a speed of 3 meters per second from one corner of a smooth, flat board that is tilted up at a 20-degree angle. To win, you must make the ball hit a small target at the adjacent corner 2.5 meters away. At what angle should you tilt the ball launcher? And for this problem, there is actually a really nice diagram located in your book on page 123. So if you guys want a visual representation, you guys can check that out. But I'm going to be going right into the axis, or my coordinate systems. So the first part of the problem, the first thing we have to deal with is we know this ball is going to be going up along this board, and we know that it's going to be coming down. The only thing that's going to be pulling it down is gravity. But, however, the board is tilted up at a 20-degree angle. So we need to find out what the force or the acceleration due to gravity is going to be for the surface of that board. So if I draw out a side view of our game, it's going to look something like that, with the surface down here, and this is going to be 20 degrees, and that's the leg of the board. Now, if this is the board like this, we know that gravity is always going to point straight down. So this is going to be our gravity vector. A common mistake is going to be people putting gravity down the actual board like that, but that is absolutely false because gravity always points straight down. Now, in order to get our component vector along this side, I'm going to make this our x-axis and then sketch our y-axis perpendicular to the x. So now we've got our x and y, and we've got this gravity vector which goes straight down, making a 90 degree here, leaving a 70 degree angle right here. So that's a 70 degree angle. Now what we want is we want this x component. So we want this x component vector right there. And how are we going to get that? So I'm going to write it as acceleration due to gravity in our problem. It's going to be, so we know if we use 70 degrees, we know we want cosine because we want adjacent over hypotenuse. So it would be cosine 70 degrees equals adjacent, which is the acceleration we're looking for, over negative 10. So because this is the g, right? The acceleration due to gravity in the downwards direction. So over negative 10. If I multiply negative 10 over, we're going to get acceleration due to gravity is going to be negative 10 cosine 70 degrees. We have that. Now for this particular problem, we need 2 coordinate systems just in order to make it easier. So I'm going to have another one sketched out like so. And for this one, this is going to be our y, and this is going to be our x. Now, we know we're going to have this initial velocity at angle theta. That's the angle that we're actually searching for, this theta, because we're saying what angle should the ball launch at. We know that the velocity of this, or the magnitude of this velocity vector, is 3.0 meters per second. And we know that we want it to travel, so the actual trajectory, the range is going to be 2.5 meters. Now, in order to solve this problem for theta, we're going to have to break it up into our y component and x component. So I'm going to list them right here. So our velocity initial along x is going to equal, so if this is our theta and we want this component vector right here, we're going to use cosine. So cosine theta is equal to adjacent over hypotenuse, so x over 3. So we're going to have 3 cosine theta. That's going to be velocity initial along x. That makes velocity initial along y equal to 3 sine theta, because we're going to want opposite over hypotenuse. Opposite over hypotenuse to get our y. And we know that our x final has to equal 2.5. And everything else starts at the origin, so we know our y initial is going to be 0 and our x initial is going to be 0. Along with, we know that x final is going to equal 0 as well, because we want it to go straight up and land. So it's gonna, because it said so where does it say it? It says that the small target is at the adjacent corner, so it's gonna be along the x-axis, no y, no magnitude for y. So now that we have those two, we're gonna start using our kinematic equations. So our first kinematic equation we're gonna use is going to be our y. So we know y final equals y initial plus velocity initial along y times t plus 1/2, and this is the acceleration along y, and normally that would be gravity, but remember we calculated it up here to be -10 cosine 70 degrees. So I'm going to put in an ag right here, t squared. And it's very important that you personalize these variables. So we know for this one we're working along the y, and later on we will work along the x. So y final, we know that's 0. So 0 is going to equal y initial is 0, so I'm not even going to write anything. Y initial along the y is 3 sine theta. So that's the initial velocity along the y-axis. And remember, we got that with the component vector multiplied by t. So t plus 1/2, and ag we calculated that to be -10 cosine 70 degrees multiplied by t squared. Now when you simplify this out, and meaning just put this stuff into your calculator, you're gonna get 0 equals 3 sine theta t minus 1.71 t squared. Now this equation, we want to set it in terms of t, just so we have a variable for t. So I'm gonna, not a variable, sorry, but so we have a value for t in terms of theta. So later on we can put that into our x kinematic equation. So I'm going to add 1.71, so I'm going to be 1.71 t squared equals, equals 3 sine theta t. If you divide by t on both sides, and then I'm going to divide by 1.71, I will be left with t equals 3 sine theta divided by 1.71. And you guys saw how I solved for t there in terms of theta. So later on I can use that in my x kinematic equation. So the last part of this is we're going to be using our x final equals x initial plus velocity initial along x t plus 1/2 ax t squared. Now, as with any other projectile motion, we're going to be having 0 acceleration along the x. So this ax is going to be 0, and all this just becomes 0. And we know our x final up here is 2.5 equals x initial was just 0, and velocity initial along x is 3 cosine theta multiplied by t, but this time I'm going to multiply it by this t. So multiplied by 3 sine theta divided by 1.71. Now I'm just going to simplify this out, so I'm going to multiply by 1.71 over there. So I'm going to be left with 4.275 equals 3 cosine theta and multiplied by 3 sine theta. Now, the next step that I used was I just plugged this equation into my calculator, obviously substituting the thetas for x's, because our button on the calculator actually says x, theta, or n, so if you click that, you're going to get a variable, and it's probably going to just show x. So plug that in for x, and then make another y equals for 4.275, and where those two graphs intersect, you're going to get a value for theta. So if you go up, you're going to get theta to equal 54.1 degrees. And that is the answer. Now, I know some of you are going to start freaking out and start telling me that that's not the answer our instructor gave us, but we have to remember that whenever we're doing projectile motion, you can always have two thetas. So one is going to be your original theta, or you could have 90 minus theta, which will give you the exact same range. So 90 minus 54.1 is going to be 35.9 degrees, equal to theta. So both of those are possible answers. And I know our instructor got 34.2, but this is within the 5% error because I just did it a different way. But I guarantee you, if you do all this work, start off by showing your model equations without plugging anything in yet, draw out your coordinate systems properly, customize your variables, and just, if you display the answer either 54.1 or 34.9, you'll get full credit, and good luck on their test.